Welcome to section 4.5, and the good news, this isn't near as long as last week, and the bad news for me is that out of the 8 problems that I've got listed there, we're actually going to throw 2 of them out. So I will tell you on Monday the day or the problems that need to be thrown out for homework as well. So here we go. We begin with problem number 1. And we are given this diagram where this is the point 0y and this is the point x0. And we know that this is 21 units long. And what we are going to do is we're going to show that this area in here is the largest whenever y equals x. Now the first thing we have to do is determine what would the area be. Well, that's not terribly difficult. The area, since this is a triangle, is 1/2 the base times the height, or 1/2 xy. But at the same time, we see that this should follow the rules of the Pythagorean theorem as well, and so we can actually say that x squared plus y squared is going to equal 21 squared. And so we get x squared plus y squared equals 441. And so x squared would equal 441 minus y squared. And so x could actually be written as the square root of 441 minus y squared. So now what we can do is we can take this and plug it back into this. Now realize the reason we have to do this is because in order to maximize stuff, which is what we're trying to do, we're trying to maximize the area, we need to get this down to one variable. Well, now we can do that. So we know that the area will equal 1/2. Okay, instead of x, I'm going to put in the square root of 441 minus y squared times y. And just to avoid confusion, I'm going to put the y out here. And so we need to find the derivative of this, because to maximize something, we take the derivative of it. Yet another example of how to use derivatives. And so in order to do that, I'm going to first of all write this in user-friendly form. Y over 2 times 441 minus y squared raised to the 1/2 power. So now I'm going to take the derivative of my area to determine what is the maximum here. Okay, leave the first one alone and multiply by the derivative of the second. Well, the derivative would mean the exponent, the derivative of the inside, which is negative 2y, and then it's the whole expression changing the exponent to whatever was necessary, plus, okay, take the derivative of y over 2, that's 1/2, and then leave the second one alone. And so, cleaning this up, let's see, this 2 will cancel with one of those 2's. We get the fraction where square root of 441 minus y squared is in the denominator. And it leaves, what, negative, okay, there's going to be a 2 down there, and negative y squared. Plus, this becomes the square root of 441 minus y squared over 2. So now we look at the common denominator. The common denominator will be the 2 square root of 441 minus y squared. So when I do that, this is what I get. I get 2 square root of 441 minus y squared. We don't have to do anything to the first fraction, so that's minus y squared plus, but we have to multiply this square root of 441 minus y squared times the square root of 441 minus y squared, which is 441 minus y squared. And combining like terms, we get negative 2y squared plus 441 over 2 times the square root of 441 minus y squared. Now, just like we have been doing for several weeks now, what we have to do is we have to get the set the numerator equal to 0 and set the denominator equal to 0. And so we get negative 2y squared plus 441 equals 0. And 2 square root of 441 minus y squared equals 0. So let's see, subtract 441 here. And divide both sides by 2. Negative 2, that is. Then take the square root. Now realize, since we're talking distance, we are only worried about the positive. So we have y equals the square root of 441 halves, which, if you remember, square root of 441 would be 21 over the square root of 2. Okay, so that's one possible answer. Then here, if we divide both sides by 2, we get square root of 441 minus y squared equals 0. Square both sides. 441 minus y squared equals 0. Add y squared. 441 equals y squared. Or y would equal 21. Now realize this 21 is not going to do us any good, because the entire length of the beam is 21. So we can throw this out for practical reasons. Y can't be 21 because then there wouldn't be any area whatsoever. We can think that through, or we can also put it into the number line. So if we go ahead and put this into the number line, we would have at 21 over the square root of 2, or at 21. And so I can choose the value of 1. Let's see, 21 over the square root of 2, I should be able to do the value of 18, and then the value of 22, say. And then if I plug it back up, way up here into my a prime, if I plug in 1, I get I'll get a positive in the denominator, and what do I get? If I plug in 1 here, I'll get negative 2 plus 441, that's positive. This is positive, so that will all be positive. If I plug in 18, I get negative 2 times a fairly big number. This will be negative, and this will be positive, so it'll be negative after that point. And then, of course, if we plug in, say, 22, this becomes a big negative. Well, negative 22 would force this to go into imaginary numbers. So that's not even a possible answer for that one. So what we know is that at 1 it's increasing, and at 18 it's decreasing, and this one doesn't really apply because it's out of the domain. Which should make sense. We can't have it 22 if our hypotenuse is only 21. So here we go. We know that this right here is a maximum, and we know that's what y is equal to. So y is equal to 21 over the square root of 2. Now we have to go way back to one of the first parts of this problem that we did, and that is to figure out what x would equal. And we know that x is equal to the square root of 441 minus whatever y is squared. Well, now, this will equal the square root of 441 minus, 21 over root 2 squared is 441 over 2. And 441 minus 441 over 2 is 441 over 2, which equals 21 over the square root of 2. So we have shown that the maximum y value is this many units. X is the exact same number of units. So we have shown that to maximize the area, x must equal y. Okay, we're now going to skip number 2. Number 2 is a whole lot more difficult. One thing I do want to point out about number 1 is that if you have a triangle like that, the maximum area will always be when the two values, the two legs, are the same length. Okay, number 3. Number 3, we basically have this drawing here, getting rid of all the pretties and everything else. Okay, we know that this is 8 feet. We know that from here to here is 27 feet. And that's about all we know. And what we want to know is what is the shortest length of this beam right here. What's the shortest length, the minimum? Well, to find either the maximum or the minimum, we have to find derivatives. Now we also have to realize that these are similar triangles. We have this big triangle here compared to this little one here. So what I'm going to do is I'm going to assign the building height to be y, and this little distance here to be x. And so what I get with the little triangle, I know if we compare 8 compared to x, that would have to be the compared to y with the entire length here, which is 27 plus x. And so I've got this combination. I'm going to do cross products, and so I get x, y equals 8 times 27 plus x, which of course this is equal to 216 plus 8x. And then I'm going to get y equals, dividing both sides by x, 216 plus 8 over x, or 8x, all over x. And so that's what my y is going to equal. So anytime I have to use y in the future, I'm going to use this not so fun expression in its place. But realize, once again, we have to get it down to one variable. So right now I'm putting everything in terms of x. X, whenever I need x, I'm going to use x. Whenever I'm going to use y, I'm going to use this expression instead. Okay, now we look at the entire beam. We want to shorten that. We want to shorten its length, minimize its length. So if we look at the big triangle, we see this should conform to the Pythagorean theorem. And so the beam squared would equal y squared, but I'm not going to use y, I'm going to use that squared plus the bottom, the ground. So that would be 27 plus x, the quantity squared. So in other words, the beam, if I square root both sides, is going to equal the square root of all this, 216 plus 8x all over x, quantity squared, plus 27 plus x squared. Now that's how long the beam's going to be. Okay? So what I do now is I'm going to actually set this equal to 0 and solve. But trust me, this is just a royal pain. So what we're going to do is we're going to put this into the calculator and determine where does x equal 0. That's basically what we're asking. Where does this whole mess equal 0? And as it turns out, it's actually a very nice number. X happens to be 12. Once we plug this into our graphing calculator and determine where is x equals 0, or where's the x-intercept, it's at x equals 12. Now with that in mind, since we know x equals 12, we can now calculate y. Y would equal 216 plus 8 times 12 all over 12, which ends up equaling 26. So now we still haven't answered what the beam is. You know, we haven't determined exactly how long the beam is. But now if we look at the big triangle, we know that the y value is 26. We know that x is 12, but that only represents this first part of it. So we need 12 plus 27, which is 39. And so then, finally, if we use the Pythagorean theorem, we would find that this would equal the square root of 1,517. Just taking 39 squared plus 26 squared and taking the square root. And so the shortest distance would be the square root of 1,517 feet. So in this section, what we're dealing with is maximizing things and minimizing things. And regardless if you maximize or minimize, you use the derivative. Now realize I really should have, after finding x equals 12, I should have put 12 as a mark here and tried to say the number 10 and the number 14 or whatever, and plug it back into this length for the beam. But you know, oh well, we're good. Actually, this case, we didn't even use the derivative anywhere, so truly it isn't needed in this particular case. Number 4. Number 4, we have a spring, and it's pulled 10 centimeters back from its rest position and released at time t equals 0 to roll back and forth for 4 seconds. Its position at time t is, okay, so we know S equals 1 minus 10 cosine of, and this is intended to be pi t, like that. It's missing the parentheses. What is the cart's maximum speed? Well, maximum speed, that's velocity, and we should know that if we have s, or the position, the velocity is just the derivative of s. So we take the derivative of this, and we have to understand there's a chain rule that's going to be playing a part here. So we take, first of all, the derivative of 1 is nothing. The derivative of cosine is negative sine, so that's going to change the negative 10 to a positive 10. Positive 10 sine of pi t, but we can't forget to take the derivative of this inside, which is pi. So the velocity is 10 pi sine of pi t. Now what we're trying to do is where is this at its maximum? Where within the first 4 seconds, from 0 to 4 is what we're worried about. That's where the 4 seconds comes into play. So what we need to do is we need to find out what are the cutoff points, I guess. 10 pi sine pi t is equal to 0. So if I divide both sides by 10 pi, I still get sine of pi t equals 0. So that means since I know sine is equal to 0 at, let's see, that would be at 0 and pi and 2 pi and 3 pi, any multiple of pi, 3 pi, so on and so forth. So I can divide everything through by pi to figure out what my time will be. So my time will be at 0, 1, 2, 3, and 4. That's where my velocity will be at its maximum. Or first of all, that's when. That answers the second question. When is the cart moving that fast? At 1, 2, 3, and 4 is when it's going to be doing that fast. What is the cart's maximum speed? Well, all we have to do is put in 1 into the velocity here, and we get sine of pi, which is 0. 10 times, ooh, that's not so good, is it? Wonder where we're going wrong here. When is the velocity the biggest? Ooh, major problem here. In order to find when the velocity is biggest, we have to take the derivative of velocity. So, we need to find the derivative of velocity. Well, derivative of velocity is acceleration. So we need to take the derivative of this again. So this would be what? Taking the derivative would be 10 pi cosine of pi t, but I have to remember to multiply by pi, so that becomes 10 pi squared. And then we set this equal to 0. 10 pi squared cosine of pi t equaling 0. Divide both sides by 10 pi squared, so cosine of pi t equals 0. And cosine of 0 equals at pi over 2, 3 pi over 2, so on and so forth. So that means pi t would equal pi over 2, 3 pi over 2, so on and so forth. And so dividing through by pi so that we figure out what time it is, divide everything through by pi, we get 1/2, 3/2, 5/2, and 7/2. And then the next one would be beyond the 4 seconds. So this is the time when the velocity will be at its maximum. What is the maximum speed? Well, now we need to plug in one of these values back into the velocity. So I'm going to plug in, just for ease, the 1/2. So velocity at 1/2 would be 10 pi times the sine of pi over 2. Well, pi over 2, the sine of pi over 2 is 1. And so that would be 10 pi times 1, or 10 pi. Let's see, 10 pi centimeters per second would be the label there, because we're talking centimeters and we're talking seconds. The time, to answer the second question, would be at 1/2 seconds, 3/2 seconds, 5/2 seconds, and 7/2 seconds. And then what is the magnitude of the acceleration? Well, the magnitude of the acceleration, we can plug it in here, or if we think about it, these values gave us 0. So the acceleration will always be 0 centimeters per second squared. And that really should make sense, because once it's done all of its acceleration, its positive acceleration, it's going to be at its fastest speed. Because then from then on, it's going to go to a negative acceleration, and negative acceleration all of a sudden starts slowing you down. So that makes sense. So if you think about this carefully, what acceleration means, then all of this does truly make sense once I get the correct problem going. Okay, now we're ready for number 5. Example 5. Okay, a rectangular field is to be enclosed on 4 sides with a fence. Start with a drawing. If you don't start with a drawing, I really don't feel sorry for anybody that doesn't understand this. Fencing costs $8 per foot for 2 opposite sides, so I'm going to just say this will be the $8 side. And $5 per foot on the other side. Find the dimensions of the fields that have an area of 760 square feet. That would be the cheapest to enclose. Now, if you think about this, my longer sides better be the cheaper material. So at least my drawing makes a little bit of sense. But now, we'll deal with this 5 and this 8 a little bit later. Right now, we just need to deal with a generic rectangle. We'll call this the width and the length. And we know that the area is equal to length times width. Well, the area we know is 760. And I'm going to just put 1 in front of the other, or 1 in terms of the other. So I'm going to let the length be 760 over W. So I'm going to put everything in terms of W. Now, we are trying to minimize the cost. So what we need to do is we need to come up with what would the cost function be. Well, the cost would be 2 of these, two W's, since that's what I'm showing right here. 2 W's, but they cost $5 a foot. Plus, the shorter ones is L times 8, but I'm not going to use L. Instead, I'm going to use 760 over W. So that would be 760 over W. I need 2 of those, because I have 2 sides, and those are going to cost $8 per foot. So now I'm just going to clean this up a little bit. This is 10W plus, okay, what is this good old number here?